Alright, hello class. In this video, it seems like it's going to cover a lot, and in a way it kind of does. We're going to be talking about lengths of curves, curvature of curves, and normal vectors. I like to think of this as the vector-valued function wrap-up. Alright, the VVF wrap-up. And to me, a lot of this kind of I want to at least give this as an introduction for the time being. A lot of this stuff we're going to come back to later. Some of it we might not, but these are all things that you should probably at least see once when you're talking about vector-valued functions. So the lengths we will definitely talk about. Again, the normal vectors, definitely. Curvature will come up as well, but maybe in a different setting. Anyway, the reason these are all lumped together, the book already lumps two of them together, and to me that third one might as well be as well, because a lot of this just comes down to, here's the formula of this thing. Use the formula to calculate the thing in different environments, in different situations. Okay, so we're going to start with the lengths of curves. All right, so we're going to start, like I said, with length of curves, and this will actually probably be very familiar to you if you remember talking about the length of curves in Calculus 2. So what we're talking about now is we're extending that idea to vector-valued functions. So if we have a vector-valued function, say r of t, and we're looking at it from, say, t equals a to t equals b. Okay, how we go about doing this is we want to measure the actual length of this curve, right? And how we do it is we split it up into a bunch of smaller lengths. Okay, so we chop it up. And in equal lengths. So we're going to call the lengths, let's say delta S, and the total length from here all the way up to here, we're just going to call S. So we're going to let S be the length, or total length. Okay, and we chop it into a bunch of pieces called delta S. So we're just chopping it. Like this would be, say, S1, S2, S3. We can think of those as points that we're chopping this along from. Anyway, if we zoom in on one of these, right, and get a closer look, what I'm going to do is, let's say S is this actual length here. Okay. I'm going to create a little right triangle. Okay, I'm going to call this delta. So if this is going from, say, a point along R, say R sub k to R sub k plus 1. All right, I'm going to call this delta x sub k, and this will be delta y sub k. All right, and we can get the length of this here. I'll call that L sub k. All right, so L sub k, well, from the Pythagorean theorem, or just what we've established before, just the length of the vector from this point to this point, it's going to be the square root of delta x sub k squared plus delta y sub k squared. Okay? So here is the idea. If we let delta s get small enough, this length is going to approximate, let's say, this length. Okay? So what ends up happening is each one of these little lengths that we chop up is going to be approximately equal to this L sub k. So each S sub k will be approximately equal to L sub k. So the total length, okay, is going to be approximated by the sum of all these L sub k's. K going from 1 to n, whatever, however many we have. All right. Now, what I'm going to do is notice that we don't have, notice that we don't have a delta t, so these are changing with respect to t. So what I'm going to do is for each one of these, take a delta t over delta t. Okay, so what ends up happening when I do that over here, so L sub k times delta t over delta t, that'll be the square root of delta x sub k squared plus delta y sub k squared times delta t over delta t, and I'm going to bring this delta t into the square root, and to do that it ends up being, and I'm just, all right, and I said I'm splitting this into delta s's, but really what I'm doing is I'm splitting it across the exact time steps. I am sorry about that. I don't think I explained that well enough. Because these little s's are going to be different lengths, but we're splitting it up across equal time intervals. I apologize for that. But when I bring this delta t in, it's going to become a delta t squared, and this ends up being, if I move this across, basically delta x sub k over delta t squared plus delta y sub k over delta t squared times delta t. Okay? So that means the total length is actually approximated by this. Okay, now that means, and now we're going to apply the integral to this. So if I actually let delta t shrink to 0, that's going to let n go to infinity. So the total length will actually be equal to the limit as n goes to infinity, okay, of this sum here. So it will be delta x sub k, and I'm just going to rewrite. Okay, so we get the limit as n goes to infinity of this sum of all these square roots, but as delta t goes to 0, this whole thing, and this goes to infinity, this actually becomes the integral. It becomes the integral from a to b, the square root of, well, delta x over delta t, as delta t goes to 0, becomes a derivative. So this is actually going to be x prime of t squared plus y prime of t squared dt. So this is actually what I was talking about last time, about how our notation could get super cluttered if we put every of t. So typically I just do the square root of x prime squared plus y prime squared dt, just to make it easier to read. Okay, and that's going to be the total length. Oops, sorry, the dt should not be inside the square root. And that's going to be the total length of the curve. All right, so let's take a look at an example. And before I do, this also carries over in exactly the same way in 3 dimensions. Okay, so the length of the curve from t equals a to t equals b is actually the integral of the square root of x prime squared plus y prime squared plus z prime squared. Well, if we look at these two formulas here, it turns out that actually the length is just the definite integral from a to b of the magnitude of the velocity, right? Or r prime, right? It's just the magnitude of r prime. Okay, I find that a very interesting result, that all we do is integrate the magnitude of r prime, or the velocity, and that will give us the length. And that kind of makes sense, because what we're doing is we're measuring sort of the velocity or the speed that's traveled over a certain amount of time. That typically gives us a displacement, or total distance traveled, right? So let's look at an example, and then we'll start talking about, say, curvature and normal vectors. All right, so let's find the length of the helix. Well, again, the length of the helix, cosine t, sine t, t, for t ranging from 0 to 2 pi. So again, this whole section here is all about, okay, what formula do we need to use? Just use the formula. So I'm going to write the formula down here. The length is the definite integral from a to b, the square root, or actually let me just say instead of that, just the magnitude of r prime dt. All right, so we just need to find the magnitude of the derivative. So first let's find the derivative. So r prime of t is going to be negative sine of t, comma cosine of t, comma 1. Okay. Now we need to find the magnitude, right? We need to find the magnitude and put it in the integral. So let me write the steps I'm doing over here. Okay, so we started by finding the derivative. Now we're going to find the magnitude of the derivative. So the magnitude of the derivative will be the square root of the first component squared. So that would be sine t all squared, plus the y component squared, plus the z component squared. Okay, so this is going to be sine squared t plus cosine squared t plus 1. Now thankfully, cosine squared plus sine squared is 1, so this is going to come out to be 1 plus 1, so root 2. All right, then the next step, put it in the integral. So we'll put magnitude r prime in the integral. Okay, so that means the length will be the integral a to b here, that's 0 to 2 pi. Okay. Then the magnitude of r prime, which will be root 2 dt. And I want to give you something that will speed some things up for you. If you're ever integrating a constant, like if you're integrating from a to b of just c dx, for example, it's literally just going to be the constant times b minus a. Right? Because what happens is it's just c x from a to b, which when you plug that into, you'll have c times b minus c times a. When you factor out the c, you just get c times b minus a. Okay? So this is just going to be the square root of 2 times 2 pi minus 0. So we'll get 2 pi root 2 as the length of this curve. All right, let's, for a second example, let's find the length of t squared comma t cubed for t between 0 and 4. So I didn't name this, but let's name this r. Okay, so to find the length, remember we need to find r prime. So r prime will be 2t, comma 3t squared. Then we need to find the magnitude. So let's find the magnitude. So that'll be the square root of the first component squared plus the second component squared. All right, and let's simplify this a bit because we're going to have to integrate this. So I definitely want it to look nicer if I can get it to look nicer. This will be 4t squared, and this will be plus 9t to the fourth. All right, and it looks like we can take a t squared out. So this will, when we factor out the t squared, we can then take it out of the square root as a t. And so we'll have t times 4 plus 9t squared. Okay, and I'm going to rewrite this as t times 4 plus 9t squared to the, whoops, jumping the gun a little bit there, to the 1/2. Okay, so the length is going to be the integral from 0 to 4 of t times 4 plus 9t squared to the 1/2 dt. Okay, and this will be a u substitution, but again, instead of a u substitution, what I'm going to do is a quick u substitution. So to do a quick u substitution, I'm going to leave the t, and then I'm going to pretend this stuff isn't there. U to the 1/2 is going to be, or the stuff to the 1/2 will be the stuff to the 3/2 times 2/3. Okay, remember you always multiply by the reciprocal, and then I'm going to divide by the derivative of the inside, and the derivative of the inside is going to be 18t. And the only reason this works is because the t's cancel. Okay. All right, so now this should simplify down to 1/27 times 4 plus 9t squared to the 3/2. And then we're going to evaluate this between 0 and 4. So we'll get 1/27. When I plug the 0 in, we're just going to get 4 to the 3/2. Then minus 1/27. And when we put the 4 in, I'll get a 9 times 16. Plus 4, which will be 148. Okay, and this really isn't going to simplify down in a nice way. This would. All right, this would just be 8/27 when we simplify, but this is not going to. So I'm just going to crank it out in a calculator and see what length we. And I want to apologize. I just realized I had these reversed. Bit of a mix up on my part. You know, you plug in the 4 first. So I'm sorry about that. So it should be the 1/27, 148 to the 3/2 minus this 8/27. And when you calculate that in your calculator, I ended up getting about 66.39, just depending on how I rounded. All right, so there we go. There's another example of this. And honestly, with these formulas in this particular section, it turns out since the formula itself is so complicated, the types of things you'll be seeing in the homework will also be about at this same level. All right, next I want to talk about curvature. Now, curvature, it's actually one of those situations where the word kind of explains what we're doing. The curvature measures really how curvy a graph is. All right, so that's essentially what it's doing. It gives a higher number when the graph is curvier and a lower number when it's straighter. And what it's essentially doing is it's splitting things up and comparing within the exact same length of curve. So we split up, say, the length of curve, and what we do is we look at, so let me zoom in on these. All right, so here is one of our curves, and here's the other, and these curves have exactly the same length. Okay, so suppose they have the length S. Okay, so what we end up doing is we look at the unit normal vector at one endpoint and the unit normal vector at the other endpoint. Okay, versus here, right? And then we compare them, because here there's a huge difference between these two, right? The difference is pretty massive versus here, which is pretty small. Okay, so that is what the curvature is basically measuring, is that difference between the unit tangent vectors within the same small interval along the curve. Okay, so let's get to what the formula is. All right, so the curvature of a vector valued function at any t is given by the following formula. It's essentially the derivative of the unit tangent vector divided by the velocity vector, or r prime. So capital T prime divided by r prime. Now there are a couple of other formulas that you could use for this, but we're basically just going to look at this one. And essentially that's what it's comparing. It's comparing how the curve itself changes versus how the unit normal vector is changing at the same time. All right, so what I want to do for this one is go back to one of the examples we were looking at before. All right, so let's take a look at an example, specifically here for t, comma, l and t. So we want to find the curvature, which is always, well, maybe not, it's always a function of t. Okay, so remember, I'm going to write down the formula again. It's the magnitude of capital T prime over the magnitude of r prime. And this is where things get kind of nasty, because this formula looks kind of inconspicuous, but it turns out at the end of the day being a real pain to deal with. So, all right, what we need to do is, there are a lot of things we need to find. Okay, so first we need to find r prime. Okay, so r prime, well, we just differentiate term by term. So r prime will be 1, comma, now it's the natural log of stuff, so that will be the derivative of the stuff over the stuff. So it will be cosine t over sine t. All right, now that I'm going to rewrite, instead of cosine over sine, that's cotangent. All right, now I need to find the magnitude of r prime, because that's what we need for capital T. All right, so the magnitude is going to be the square root of 1 plus cotangent squared t. All right, because 1 squared plus cotangent squared t. Now, here, so here we could try to continue from here, but here's my advice. 1 plus cotangent squared t, that is going to be, using the Pythagorean identity, okay, is going to be cosecant squared of t, which will, since we're taking the square root, become cosecant of t. And specifically, it's the absolute value of that. So I'm actually just going to drop the absolute values and just only choose t's where this is positive. So I'm going to choose t's where cosecant t is positive. Specifically, that should be t's, or not equal to, can't equal 0, but t's between 0 and pi over 2. Right? Because if you're unfamiliar with cosecant, you don't know it very well, remember it's 1 over sine. So if you graph sine from 0 to pi over 2, cosecant does this. It has vertical asymptotes where sine is equal to 0. So we're basically going to restrict it between 0 and pi over 2. Okay, so that is r prime. Now I need to find capital T. Well, capital T is r prime over the magnitude of r prime. And this is why I wanted to simplify this down as far as I could, because now that means I have the vector 1 over cotangent of t divided by cosecant of t. Well, when you divide by cosecant, that's the same thing as multiplying by sine. And actually, this ends up being a good example because we haven't really looked at scalar multiplication when it comes to vector-valued functions, but this here, this is a vector-valued function. This is a scalar function. Okay, so you can bring this in term by term, and now I have the vector-valued function sine t, comma, sine t times cotangent t. Okay, well, cotangent is sine over, or sorry, not sine over cosine, but cosine over sine. All right, so we'll just cancel those signs, and so we end up with the vector, finally, sine of t, cosine of t. So that's our capital T. All right. Now, we're still not done because the curvature formula, as I said, just looking at it, it doesn't look that bad, but now we have another step. We got to find the magnitude of t prime. So we found t, now we need to find t prime. Okay, so t prime. Well, thankfully now we've simplified this. If you didn't simplify this up here, you'd be in for a world of hurt by the time you got here. And if you don't believe that, try it with leaving it like this and seeing what happens. Okay, but we'll get the vector cosine t, negative sine t. All right, and then from here, that's t prime. We need to find the magnitude of t prime. Which in this case will just be 1 because we got this down to, it'll be cosine squared t plus sine squared t, which will be 1. Okay, we have all the pieces we need. So now the curvature, right, is going to be the magnitude of t prime all over the magnitude of r prime. So the magnitude of t prime, thankfully, came out to be 1. The magnitude of r prime, that's actually off the screen now. That was over here. That ended up being cosecant of t. All right, so 1 over cosecant t is sine of t. So the curvature function ends up being sine of t. Only though for t between 0 and pi over 2, not including those values. And actually that's going to make sense because if we looked at our original vector valued function, we have ln of sine, and that was going to cause trouble if we ever tried to plug zeros or negative into ln. So we were already restricted, and we could have already said up here that this had to happen. Okay? All right, so let's actually look at this on a graph and see what's going on. And I'm coming back here because before we go to the graph, it's not pi over 2. Sorry about that, it's pi. Yeah, I must have been thinking of cosine, but yeah, it's pi. I don't know what in the world came over me there, but sorry about that. Glad I caught it here, but yeah, it's 0 to pi. Again, very sorry. All right, so here's the graph of the vector valued function itself. It has asymptotic behavior, and it moves in this direction. So I have it set up to where as time goes on, so we're starting, actually maybe I should just put a t value down. Let me do that. Okay, so we're starting at t equals 0.01, and we're going to let it cruise around, and you'll see the k. So here, and when t is equal to 0.01, our k is equal to 0.01. And as time goes on, we see that here the curvature jumps up to about 1 and then starts to decrease again. Okay, and then whoop, gets down to really low values. So if I'll speed it up here to get through here and then slow it. Actually, let me just control it with the slider here. So when we get to here, we see now it's about 0, closer to 0 again. But if we swing it around this way, it hits about 1 and about 1.5. Okay, or 1.56. That's going to be pi over 2 is when it's actually equal to 1. Okay, and then here, as we can see, what's happening is, so hopefully here you can kind of see the gist of how the curvature works. And again, that formula, though it looks, not that bad, it ends up being a real beast to deal with given the situation. Okay, so the next thing to talk about, and again, this is just one of those situations where we have a formula and we just use the formula, is the principal unit normal vector. Okay, so what is the principal unit normal vector? Well, what that ends up being is it's called capital N, and it ends up being the vector t divided by its magnitude. So it's sort of the same idea as t is to r, but n is to t. All right, so what does this do? Well, n is a vector, there's a unit vector that's perpendicular to t. Okay, now you might be wondering, well, all right, if I have, say, a vector valued function here, and we're moving along it in this direction, okay, and at this point, say here, I've got my t. There are two unit vectors normal to t. Okay, and then if I pick a t over, let's do it here. let's say I have a t here, there are two vectors that are normal to it. So which one is n giving us? Well, n is actually a very special one. N gives us the direction that the object is turning in. So t is the vector in the direction of travel. N gives the direction the object turns in. Okay, so in this case, since the vector valued function is moving in this way, it's actually turning here. So n is giving us that, okay, t is traveling this way, but n is pushing us this way because that is the direction we're turning in. Here, okay, it's kind of hard to tell because if we're on this side here, n is definitely pointing this way. All right, because that's the way we're turning. And then eventually we'll hit a place where we don't really have an n, and then we'll come around and it will be pointing this way. So at some point, it's going to flip over to be the direction that we're turning in. Okay, so let's look at some examples of how this works. All right, let's consider the function t comma t cubed. And I'm picking that one because that's basically just our cubic function, right? That's going to be y equals x cubed, because if we put x equals t into y equals t cubed, we end up with y equals x cubed. Of course, we have a direction of travel. Okay, so we will expect our t's to be pointing in the direction that we travel, but our n's on this side to be pointing this way, and the n's on this side to be pointing that way. So let's check it out. So first we need to find t. So to do that, of course we need to find r prime, which will be 1 comma 3t squared. And then we need to find its magnitude, which will be the square root of 1 plus, this will be 9t to the 4th. All right, and so hopefully already you can see how disgusting this is going to be, because capital T is going to be 1 comma 3t squared all over the square root of 1 plus 9t to the 4th. Okay? And so to find n, we need t prime over the magnitude of t prime. Oh, man. So, okay, that means we need to find t prime. That means using the quotient rule, which I'm glad actually came up, because the way the quotient rule works still works the same way even when we have vectors. All right, what do I mean by that? Well, it's going to be the derivative of the top. So the derivative of the top will be 0 comma 6t, okay, times the bottom left alone, okay, minus the top left alone, times the derivative of the bottom. So the derivative of the bottom, we have a square root derivative, so it's going to be derivative of the stuff. That's going to be 36t cubed all over 2 times our square root stuff. All right, and we have a nice cancellation here, right? That 2 cancels with the 36 and leaves an 18. And then this will be all over the bottom squared. So 1 plus 9t to the 4th. Okay. Whew, now, you might think all is lost here, but here's what we're going to do. All right, here's what I'm going to do. I'm going to multiply the top and the bottom by this square root stuff, just to get rid of it. Okay, so it's going to get rid of this square root completely, and then when we multiply this by it, it will drop the square root but keep the stuff on the inside. Okay, and when we do that, so we'll get the vector 0, 6t times 1 plus 9t to the fourth minus 1 comma 3t squared times 18t cubed. Whew. Okay, and then the denominator is going to become 1 plus 9t to the fourth, all to the 3/2, because we have this to the 1 and this to the 1/2. When we multiply those together, it's 1 plus 1/2, and we get this. Okay, now I'm going to clean this up a little bit, and I'll spare you seeing every single step there, but we can... we're going to do some scalar multiplication, then vector arithmetic. And I just want to reestablish here, this is the quotient rule that we're applying. All right, so I just wanted to show here, I distribute this through, and when we do the subtraction, you'll notice that the 54t to the fifths will cancel out. So this is going to simplify a lot more than we maybe expected. All right, so here we are. We're down to our t prime, which is negative 18t cubed, comma 6t, all over 1 plus 9t to the fourth, all to the 3/2. So while it started off looking awful, it does come down to be something kind of nice. However, here's where things get worse. We have to divide by its magnitude. Oh no, okay, well, let's calculate the magnitude. Well, and here's where I'm going to suggest and why, or a good explanation of why I left this alone, is it's going to be the square root of this stuff squared. Well, this is going to apply to both pieces. So really, I could just factor it out. So I could say it's 1 over 1 plus 9 times t to the fourth, then 3 to the, or to the 3/2 power squared is just going to be cubed. Okay, then it'll be negative 18t cubed squared, so 18 squared is 324. T cubed squared is t to the sixth, then it'll be plus 36t squared. All right, and let's simplify this down. So here's something interesting. When we break this apart, this is just going to go right back to being 1 plus 9t to the fourth to the 3/2, and then we can actually factor some stuff out of this completely. All right, so when we factor out the 36t squared, this, what's left, should look kind of familiar. Yeah, so this, we got to be careful now. This becomes, I'll leave this like so. Here's what we have to be careful about. This 36t squared, when we take the square root of it, it becomes 6 times the absolute value of t. Okay, and then what's left is just the square root of 9t to the fourth plus 1. And this is this to the 1/2. So let me write it like that. Okay, and so this is going to cancel with this down here and simply leave 6 absolute value t all over. So the 3/2 minus 1/2 is is going to end up being 2/2, so we just get this. Now, I don't have to worry about absolute values here because this thing is always positive. Now, I know that this is getting way out of hand. Let me clear some things off and list out what we have so far. Okay, so clean this up a little bit. Now, we have everything we need for n. It's going to be t prime over the absolute value of t prime, or sorry, the magnitude of t prime. So n will be t prime divided by this. So actually, it might just be easier to say that n is t prime over magnitude t prime, which is equal to this. So it's this vector divided by this magnitude. Now, when we invert and multiply, okay, when we invert and multiply, we get this. All I've done is flip this denominator over, and the 6 is going to simplify nicely to give us negative 3t cubed, comma, t. And then this guy is just this guy. So this is to the 2 halves, 3 halves. So this becomes the square root of 1 plus 9t to the 4th. And we still have this over the absolute value of t. So what that's going to do is, well, when we have to be a little careful because here t over absolute value of t, well, that's just either going to be 1 or negative 1 depending on whether t is positive, and we'll have a similar thing going on here. So let's go to a graph and I'll show you through the graphs what's going on here. All right, and I know this was complicated. I did want to show that though these formulas look inconspicuous, they look like they wouldn't be that bad, they are. Okay, so here's the graph. I know that was a big pain, but we're just going to look at the graph now. Here is the path of the cubic, and we're just going to let it go. And you can see that t is pointing in the direction that the function is traveling in, or the curve is the point is traveling in, and n is pointing in the direction that the object is wanting to turn in. And you'll notice, let me move it here, right at 0, there is no n. And that's because if we look back at our formula for n, when t is equal to 0, we're getting division by 0. Okay? And so n is undefined, so we don't get an n. But when we take a step forward, we get n is now pointing up, right? Because now that's when the object starts turning this way. Whereas one step behind, it's still pointing down because that's the direction of turning. Okay, so that is what the normal vector does. And unfortunately, the formula is just a real beast unless it's something extremely specialized. All right, I want to show another graph real quick. I'm not going to go through the formula, but I just want to show it based on one of the previous examples we saw in the one of the previous lectures. All right, here's that last little example I wanted to show of this particular guy. I don't have it set up to where n should disappear when it needs to, but as you can see, and I've labeled it as m instead of n here, but we see that t is always pointing in the direction of travel, while m is always pointing in the direction that the object is turning in. All right. I always think it's much easier to see what's going on with animations. All right, so I think that's enough for this particular lecture. I know it's kind of a brain melter, but that should be the only one that's just a bunch of formulas thrown at you like this. All right, so I will catch you all on the next one. Cheers.